This is one of two videos to demonstrate how to illustrate the two approaches to hypothesis tests for means. The first is the critical value approach, shown in this video, and the other is the p-value approach. Both are shown in textbooks. The critical value approach is usually a little bit easier to understand at first, although in academic and scholarly work, the p-value approach is used almost exclusively, so it's important to be able to understand both. Now, these videos are intended for students who already understand the formulas and definitions of all of the key things that you need to calculate, but it becomes a little bit more intuitive if you can put all of those calculations and symbols and numbers into a single picture to show what a hypothesis test is doing. On this picture, we start with a normal distribution or a bell-shaped distribution. It actually may not be the normal distribution. It could be the t-distribution, which looks very similar. And over here we've got two hypotheses. The null hypothesis is the one that we say that we're testing. We're going to assume that this is a two-tailed test, meaning the null hypothesis is that the population mean is equal to a specific number. For no particular reason, let's assume it's 60. And the alternative hypothesis is everything else. So if the null hypothesis says that the population mean is equal to 60, the alternative hypothesis is that it's not equal to 60. We're going to use a significance level, often signified by the Greek letter alpha, of 0.05 or 5%. And that's all the information I'm giving now, because a really helpful idea when you're trying to comprehend what a hypothesis test is doing is to not worry about any of the data or the statistics or the calculations until after you've set up your picture. Now, in the critical value approach, we use that null hypothesis and our significance level to draw a rejection zone that's defined as the area beyond a critical value. And for alpha equals 0.05, these critical values are either a z or a t value from the z distribution or the t distribution that has alpha in the two tails. So for this two-tailed test, because the alternative hypothesis can go in both directions, either bigger than 60 or smaller than 60, we take that alpha of 0.05, split it in half, and we find a value from the t distribution with a particular number of degrees of freedom, or the z distribution that has 2.5% in the lower tail and 2.5% in the upper tail. If you remember your values from the z distribution, the empirical rule says that about 95% of values are between a z of -2 and a z of +2. More accurately, it's 1.96. So for that common value of alpha equals 0.05, meaning 5% in the tails, 95% in the middle, this critical value of z would be 1.96 negative, and over here 1.96 positive. If you're using the t-distribution because you don't know the population standard deviation, then your t critical value will be a little bit bigger than 1.96. It could be 2, could be 2.1, could be 2.5. That all depends on the number of degrees of freedom that you have. Now, this rejection zone means that while you were expecting, at least according to the claim or the null hypothesis, that the population mean is 60, when you go out and collect your data and you get a sample mean to estimate the mean of all possible values, you might get 60. However, you might get 59, you might get 58, you might get 62. If your sample mean is significantly different than 60, that is, not just a little bit farther away from 60, but a lot, then that gives you some sort of evidence that the null hypothesis is wrong. Now, that's the same as saying calculate a z or a t statistic, which is different than a critical value, corresponding to your sample mean, and if your t or z statistic is beyond this threshold or this limit, that is, it's in the rejection zone over here, then your value, your sample mean, was not just far away from 60, but so far away from 60 too many standard errors, that 60 is likely to not be the correct value. So suppose we go out and collect our data, and we get a sample mean of 56.5. Notice that is 3.5 units below what we expected according to the null hypothesis. And suppose we get a standard deviation of 10, and we get a sample size of 25. That means that your standard error is s over the square root of n, which is exactly 2 because I picked nice numbers. Now that means that this 56.5, which is 3.5 units below the expected mean of 60, in terms of standard errors, 3.5 units below 60 is 1.75 standard errors below 60. Remember, a standard error here is 2, 10 divided by the square root of 25. Well, if our critical value here is, say, 1.96, or we'd probably need a t-statistic for our critical value here with a sample standard deviation and not the population standard deviation. Perhaps this critical value is -2, maybe it's -2.1. Our sample is below 60. However, it's only 1.75 standard errors below what we expected. That is, it does not fall in the rejection zone. So even though our sample indicates that the true mean is not 60, it's probably closer to 56.5, it's not so far away from 60 that we can conclusively say that 60 is wrong. That is, because our test statistic did not fall beyond our critical values in these rejection zones, we do not have substantial enough evidence to reject the null hypothesis. And if somebody really wants to try to convince you that 60 is the true mean, you don't have enough evidence to say that they're wrong. Now we can do the same sort of thing for a one-tailed test. So let's use the same numbers we had before. Here, though, the null hypothesis is that the true population mean is 60 or greater. And if we find a value that isn't just less than 60, but significantly less than 60, excuse me, then we should be able to reject that null hypothesis that the mean is 60 or greater and say that the true mean is definitely less than 60. Again, we'll use a significance level of alpha equals 0.05. And before we even look at any data from our sample, we can set up our rejection zones. Now again, think about how to draw this rejection zone very carefully. If the null hypothesis is that the true mean is 60 or greater, to reject that null, you'd need a value of x bar, of your sample mean, that isn't just less than 60, but significantly less than 60. That means that your rejection zone needs to not just include small values, but significantly small values. So the rejection zone needs to be a lower tail in this distribution. Because we chose a significance level of alpha equals 0.05, this rejection zone needs to have an area of 0.05. And our critical value that defines that threshold is a value from the t or the z distribution that has 5% of values below it. Now here's our data from our sample again. Suppose we got values of a sample mean of 56.5. Again, that's below 60. It seems to suggest that the null hypothesis is wrong. The question is whether or not it is so much below 60 to say that 60 or greater, that the null hypothesis is implausible. Well, we need to ask then, this value of 56.5, how far is it below 60? It's 3.5 units, and based on our standard deviation and our sample size, we have a standard error of 2. That 3.5 units is 1.75 standard errors below what you expected. Now, if you're using the z distribution, your critical value here is 1.645. If you're using the t-distribution, I think it's closer to 1.7. So your picture might look something like this. This isn't quite drawn to scale. The red line should be a little bit closer if this value here is 1.7. The red one's 1.75. But again, the rejection zone defines a threshold or a limit of how many standard errors away from what was expected is sort of tolerable. Perhaps that critical value is 1.7. So if you observe something that was 1 standard errors below what you expected, or 1.5, or maybe 1.6, that's lower than 60, but it's not so much lower that you could say that the null hypothesis is wrong. In this case, if we've got a critical value of 1.7, and our sample mean, our x bar, is 1.75 standard errors below what we expected, that's too far away. So because our test statistic is beyond our critical value, we would say that we have conclusive evidence to say that the null hypothesis is wrong. We would reject the null and say that the true population mean is likely to be less than 60. We don't know what the true population mean is, but our evidence is conclusive enough to reject that it is 60 or greater.